Good morning. I'm Praveen. So this talk is about zkRevoke. It's a protocol for addressing privacy issues in revocation of verifiable credentials. So let me briefly give a background on verifiable credentials. So verifiable credentials it contain claims about holders. Can be like name, age, role. In this example, the use cases for verifiable credentials are diplomas, passports, and employment identities. So right now, these verifiable credentials they are being deployed in private and public sector organizations such as PUDI. So first, let me briefly give a overview of the entities in the verifiable credentials ecosystem. So starting with issuer issues verifiable credentials to holders and also revokes verifiable credentials. So during revocation, the issuer usually stores proofs in registry and then holder the what holder does is holder creates a verifiable presentation out of verifiable credential and sash it with verifier and verifier verifies the proof, including verification of revocation status. So yeah, let me go to the problem. But before doing that, yeah, let me start with an use case of an employer issuing employment proof VC consisting of claims such as name and role to Bob, who is currently working at employer. And let's consider the scenario of Bob applying for a job at a recruiter. So what Bob does is Bob generates a verifiable presentation and then shares it with the recruiter to prove that he is currently employed there and recruiter checks revocation status. So in this scenario, the revocation status more or less checks whether Bob is currently employed or not. So the problem in this flow is that once a recruiter gets access to the VP, the recruiter, if it is malicious, it can continuously check the revocation status. So till the end of expiration or revocation. So essentially, just by giving the access to the VP, verifiers they have the capability to track the revocation status. So we want to address this issue in this work. So what we want is that we want Bob to restrict the verifier to check the revocation status only for a specific time period. So after that, Bob does not want the recruiter to check the revocation status. So we call it configurable period. And other than that, we also want this one-time VP sharing property. It means all the included information needed for verification that should be included in a VP. We don't want any communication between Bob and recruiter like back and forth. And other than that, we also want the verification to be unobservable by the employers. In this case, if employer knows that Bob is currently applying for a job, then it affects the working conditions. So ideally, employers should not learn anything about the interaction between recruiter and Bob. So to achieve these goals, we propose zkRevoke. First, let's give the building blocks of zkRevoke. So first, we have the tokens. So before that, what happens is that in a VC, an issuer assigns a unique seed in the VC. So seed is similar to permanent identifiers. It is also known only to the issuer and holder. So from the seed, the protocol, what we do is we generate time-bound identifiers. So in our system, we consider the time into sequence of epochs where a token identifies a VC within an epoch. So in that manner, for each epoch, there will be different tokens from the same VC. So and the issue what it does is that when VCs are revoked, it stores tokens corresponding to revoked VCs in the register. So we follow the approach of blacklist instead of whitelist for performance reasons. And since tokens are time bound, the issues also refreshes the list of tokens after each epoch. So holder what holder does is that generates tokens for m epochs and then include them in the VP. So essentially, the holder by this manner restricts the verifier to allow the verification to be done only at the specific epochs. So in this manner, we achieve configurable period and also one-time sharing. So all the information needed for checking verification of revocation status that is included in the VP. So what verifier does is that verifier fetches blacklist from the registry in each epoch and essentially performs membership check. So if a token is present in the registry, it means that underlying VC is revoked. So In this manner, it also achieves unobservable verification. So issuer is not at all involved in the process. So all the verification happens without the knowledge of issuer. So one slight problem or challenge in this approach is that holder generates token from a seed and shares it in the VP. But the verifier does not have the ability to verify the correctness and ownership of tokens. So it means that without adding any proofs, it is possible for holder to generate random tokens, fake tokens, and generate it, share it in the VP. So we solve this problem using zero knowledge proof. So essentially, what we do is that a holder generates zero knowledge proof to prove the correctness and ownership of tokens without revealing the seed. So that proof acts as a proof for the correctness of token. So we design the zero knowledge circuit consisting of following conditions. So essentially, the circuit verifies that there is a signature on the seed and the tokens are computed correctly. And the key idea is that all the private inputs are kept only at the holder side. So the holder does not share all these private values with the verifier. So in this manner, untraceability is achieved because tokens and ZK proofs for specific epochs prevent verifiers from tracking the revocation status. So yeah, let me just briefly present how it is compared against related to it. So accumulator-based protocols are predominantly used in verifiable credential systems such as Anonymous and IRMA. So they are very good at restricting verifiers from continuously tracking the revocation status. But the only problem is that they do not have the capabilities to support configurable period or one-time sharing because of the fact that to generate non-revocation proof, a holder needs the knowledge of future accumulator state because accumulators are updated during revocation. So because of that, holders have to fetch accumulator state each epoch and update the proofs and then share them with the verifiers. So let me briefly present one objective in the evaluation, whereas in the paper we do have detailed evaluation. So in this one, we compare zkRevoke against IRMA, it's accumulator-based protocol. So zkRevoke achieves lower bandwidth than IRMA because of the essentially the issue with the accumulators that construction of VPs require information about other VCs. And other than that, when it comes to computation cost, IRMA is generally faster than zkRevoke, but as more PCs are revoked, IRMA starts to become slower. So essentially, even for computation, zkRevoke performs better than IRMA. So just to summarize the list of contributions, yeah, we proposed zkRevoke system, and we also describe the proof of correctness in our paper. And we also have a detailed experimental and analytical evaluation. Other than that, we also proposed multiple extensions for supporting selective disclosure and linkability and reply attack protection. And yeah, thanks. If you have any questions, feel free to approach me during the Q&A session. Thank you.